Hello everybody, this is a lecture for nanofabrication technology. This is part of the course in International School of Engineering, Chulalongkorn University, and my name is Varong Pavarajarn. And if you have any question, feel free to email me at this email. And we are going to have about 10 lectures covering the fabrication of various forms of nanomaterials. Starting from lecture 1, this is an introduction for nanomaterials, and we will spend maybe about an hour to give you introduction and require background to study this technology. Before we start, let me give you a brief review on plane and lattice, because what we are going to focus from now on would be the crystalline materials. So you need to understand crystal structure of materials. In order to define solid to be crystalline, the solid must have order of arrangement of atoms within the structure, and that order would be defined by what we call lattice and unit cell. These seem to be points in space, okay? And from what you may have learned in the previous classes, the lattice is defined based on the smallest unit of the repetition. What about this triangle? Is this considered a lattice? If you move the lattice or move this triangle around transverse from the left to the right, from top to bottom like this, you see that the triangle does not cover the whole space in this picture. So you will still have uncovered area here, over here. So that means the triangle here cannot be considered as the lattice because it does not cover the whole area of the space. Okay, this is the yellow part is the filled space by the lattice or by the triangle, but you still have unfilled space, so the triangle is not considered as the lattice. What about this hexagon? When we transverse the hexagon up and down, left to right, you can create the whole area. Okay, the hexagon can cover the whole area, but the hexagon is not considered as lattice as well. Why? Simply because the hexagon is not the simplest unit that can create this pattern. So what is the simplest unit? In this picture, the simplest unit is this form. Okay, you can transverse it left, right, and up and down, and then you can cover the whole area. So this dotted line is considered as unit cell. Alright, so in three-dimensional space, the unit cell can be defined based on 14 forms, like so. Each form is consisted of 7 systems. For instance, cubic systems, tetragonal system, orthorhombic system, hexagonal system, and so on. In some systems, like cubic systems, position where atoms can stay are defined in various ways. For instance, the first one here is called simple cubic cell. Okay, the atoms can stay only at the corner. The middle one here is called body center cubic cell. Okay, simply we have the simple cubic cells plus one more location at the center. So on. All these systems are 14 possible ways to put atoms in space in nature. Okay, this is called 14 Brevis system. Once you understand the arrangement of atoms in space, then you have to understand plane, which give you the arrangement on specific surface. and the plane in three-dimensional space is defined by three numbers called Miller index. Miller index in this picture is I picked the cubic cells. Okay, this is cubic cells. This yellow plane is defined as 010 plane, basically because the plane intercept y-axis at 1 unit. Okay, it does not intercept x-axis, it does not intercept z-axis. So if you take reciprocal of the intersection of x is at infinity, reciprocal of infinity is 0, intersection at y-axis is 1 unit, inversion of 1 over 1 would be 1, right? And for z-axis, intersection is at infinity again, so reciprocal would give 0. So these three numbers, 0, 1, 0, are called Miller index. So you can imagine if you have different set of numbers, the plane represented by this number would be changed. Like this plane, the intersection of x and z are still at infinity, so reciprocal gives you 0. On the other hand, on y-axis, the intersection is only at half, so reciprocal of half is 2. So this plane would be represented by the number 0, 2, 0. Like so, in this plane, the intersection at x would be at 1 unit, y at 1 unit, no intersection at z. If you take reciprocal, you get 1, 1, 0. This plane would be 1, 1, 1. Alright. For this plane, you can see that there is no intersection for x-axis. Intersection at y-axis is at 1 unit and 1 unit at z. So after taking reciprocal, you get 0, 1, 1 as a Miller index for this plane. The Miller index can also be applied to any systems in 14 Breves system. Like this is monoclinic system. Basically, whenever you have a box, you take axis along the edge of the box, and then the rest will be the same considering the intersection of the box. So this would be 0, 1, 0, just like what we discussed in cubic system. But you can see that 0, 1, 0 of the cubic system and 0, 1, 0 of monoclinic system are not the same plane. So they are different based on their crystal system as well. Okay, so this would be 1, 1, 0 and so on. So in order to understand the nanomaterials, you have to be aware of scale. Alright, so if I start from 10 centimeters and reduce the size down to 2 nanometers, okay, and I would like to give you some examples so you can grab a sense of scale. If 10 centimeter is a piece of cake, this is a chocolate cake, a right size, about 10 centimeters. The 100 micrometers is the diameter of human hair. This is hair. Okay, you may have, if someone have a thick hair, you may have a hair with diameter of 200 or 300 micrometers, but in general, human hair has diameter in the range of 100 micrometers. For 5 micrometers, that's the size of red blood cell. Alright, 100 nanometers is in this picture, and this is a man doing the welding. And in this picture, size of 100 nanometers is basically fume here, a fume generated by a spark or by a welding. So this fume is basically a particles, or what we call aerosols. This particle has a size in the range of 100 nanometers. For 2 nanometers, this is a picture, scanning electron microscopy picture of DNA. This is human DNA, and inside the diameter of DNA strand is about 2 nanometers. To make you further understand the size, if I represent 2 nanometers by a piece of cake here. 5 micrometers would be the size of SUV car. So you can imagine that I can open the car, put this piece of cake inside, just like when a cell have a DNA inside. In more advanced, you can put nanoparticles with the size of 2 nanometers inside a cell relatively easily, and you can put quite a lot of numbers of nanoparticles inside, right? For 100 micrometers, that would be the size of a building, a skyscraper. Now you can imagine if you stand on the rooftop of this building, staring down to the street, you can see a particles. Let's say I put a piece of cake like this on the street. If I want to manipulate the particles, that means if I want to move the particle from one position to another on the street by standing on the rooftop of this building and try to use a long stick, try to push the particles on the surface of the street around, you can imagine that that is relatively hard, really hard, because we are standing on the scale of micrometers at least. But if you want to manipulate in the nanometer scale, that would be quite challenging. Alright, in the order of 10 centimeters, that would be the size of the moon. So that is much larger than 2 nanometers here. So this should give you an idea about how big is the world that we are right now, and how small is the particles that we want to create and manipulate. For nanotechnology, when you hear about the word, people would normally start imagining electronics. Okay, nanotechnology in the common sense are related to electronics, especially in circuit or in microelectronics. Microprocessor like Intel contains a lot of circuit with nanometer size. But you have to also understand that there are so many applications of nanotechnology. For instance, this picture is the exhaust pipe of a car. Okay, this is what we call catalytic converter. It converts exhaust gas that contains toxic gas like nitrous oxide and neutralize that nitrous oxide into nitrogen. Okay, inside there's a small particles of catalyst dispersed inside this catalytic converter. That's also considered as nanotechnology as well. That there are a lot of products in the market right now that contains nanotechnology. If I show you these pictures, which one would you imagine containing nanotechnology? Someone would say this lens because it has electronics. Of course, but if you exclude all electronics from this picture, you see that sometimes nanotechnology is hiding underneath a plain sight. For instance, this cream or lotion or sunscreen contains nanoparticles of UV absorbing materials. Okay, the smaller the particles, the smoother the cream. This ceramics pieces or toilet basically contains small particles on its glaze, so that there will be no sticking of undesired materials on the surface. This is a sensor. Of course, sensors works in nanoscale size. Okay, sensor for blood or for sugar in blood. Same thing, this is also sensor, even though it's just a pregnancy test kit, but it is one form of sensor that can also be fabricated using nanotechnology. Inside this drill, there's a battery. Inside the batteries, there's a lot of technology in there. Alright. Even the tennis ball has a surface or has a way to weave these fibers, includes nanotechnology. Okay. In nanotechnology, it started by trying to reduce the size of materials. It starts from this picture. This is the first transistor invented by Bell Lab in the US. This transistor was reduced in size and crammed up in small space to form microprocessor. Just like a Pentium Core i7, it has about 800 million transistors in size of less than square inches. Okay. Apple A13 has almost a billion transistors in size, and more advanced microprocessor chip would contains a lot more very small transistor using nanotechnology. But on the other hand, nanotechnology was also invented to enlarge surface area, especially in the field relating to chemical reactions. Because if you imagine a cube with 1 cubic millimeter, the surface area, there are 6 sides of this cube. The surface area would be 6 square millimeter. If I cut each side into 1/10, the size of the particle obtained would be 0.1 millimeter. The total surface area, if I keep the same volume to be 1 cubic millimeter, but make this particle smaller to 1/10 in each side, then the surface area increases 10 times, from 6 square millimeter to 60. If I keep repeating that, from 0.1 millimeter to 1 micron, the surface area increases from 6 to 6,000 square millimeter. If the size is reduced to 10 nanometers, then the surface area is about 0.6 square meter. The volume of 1 square millimeter, you can imagine a single grain of salt or a single grain of sugar. It is that small. But the surface area of 0.6 square meter is the size of a beach tower. So it's that large. So you can squeeze that big area into very small volume. So if the area is used for surface reaction, that means the single grain that you hold in your hand would be very active when the surface area is much higher. Alright, so right now we can increase the surface area of particles, 1 gram of particles, to have surface area as high as about 2,000 square meters, which would be very good for catalyst or absorbent or even ion exchange resin. Alright, but the popularity of nanomaterials, or the wow factor of nanomaterials, come from unique properties at nanoscale. For instance, if you consider material in micrometer scale, it should give you the same properties as bulk material in meter or centimeter scale. But if you scale down to nanometers, then the property is distinctively changed. That would be sometimes considered a bit as a benefit, but sometimes they can be constraints. Okay? For instance, if we said that the nanometer scale gold has lower melting point, it would be good for fabrication. It would be bad if your application requires high temperature. All right, because the gold, nano size gold would melt away. All right, so what is considered as nanotechnology? Basically, we try to make particles or materials to be small in nanometers so that we can use the unique properties. Okay, so it doesn't mean that anything in nano size will be considered as nanotechnology, but we want to try to improve properties by design. Okay, the way we design it is considered technology. When we use that for particles or materials with nano size feature, that would be considered as nanotechnology. So we are going to describe properties of materials in 4 ways: physical properties, chemical properties, mechanical properties, and electrical properties. All right, let's start with the first one. Physical properties for nanomaterials. The first one that people have observed is the significantly lower melting point. Just like this graph, this is the melting point of gold. If the gold has particle size around 20 nanometer, the melting point is about the same as bulk gold, which is around 1000 degrees C. But if the particle size is smaller and smaller, down to about 2 or 3 nanometers, the temperature, the melting point drops down significantly. As I said, this might be good, this might be bad, depending on the application that you want to use. Alright. The other property that is very exciting for people at the very beginning is the optical properties. For instance, this cup, this is a wine cup from Roman period. This contains nanotechnology. Okay? How? This cup has gold nanoparticles embedded inside. From outside, if you look, it looks green, because when the light hits the cup and reflect to your eyes, all the color except green are absorbed. Okay, so you can see the cup as green. But if you put the light source inside the cup and let the light passes all these gold nanoparticles, the light would excite gold nanoparticles and give up red light. So you see the cup as emitting red light. This was very cool in the old days, and Romans said this is one of the good technology, but they did not know whether they are using nanotechnology at the time. Okay. Same thing like this. This is cadmium selenide nanoparticles. We can change its color from yellow down to red by changing the size. The good thing about nanoparticles is that you can fine-tune their properties by controlling the size mainly. Just like in this picture, in all test tubes, the particles are the same in chemical composition, but the size are different, and you can see the properties are different as well. For chemical properties, so if the physical properties is depending on the size, chemical properties will depend on the size as well. Okay, for instance, mostly all the particles if the size becomes nano size, they become very active. And we will learn in lecture 2 why. Okay, they're active just like aluminum, which is inert, considered very inert metals. We use aluminum for window frame, door frame, because it does not oxidize. All right. However, if you decrease the size of aluminum to nanoparticles, aluminum are combustible. All right. Platinum, which is considered as noble metals, platinum nanoparticles now becomes reactive. Platinum nanoparticles are used as catalysts all the time. And then materials can change their phases at different temperature. And normally when the size becomes smaller, phase transition temperature becomes lower and lower. Okay? So on one hand, you can have problems dealing with stable materials because it tends to change the phase. But on the other hand, you can explore new phase of materials by simply synthesize them into nano size. Also, if you are in optical engineering, you may have heard of this word, quantum size effects. The quantum size effect means that the particles behave more like an atom. So an atom, for an atom, you can excite its energy and make them emit light. Okay? And excitation energy depends on the atoms. But for particles, now excitation, you can excite particles in the same manner as when you excite atoms. But now for particles, excitation energy depends on the size. Like this, these are nanoparticles that has been excited by light source, in this case a black light, okay, or UV light. When it excites, and de-excitation of an electrons or energy down to the ground state emits light. So you can see that different light here means that nanoparticles have different excitation energy. Okay, and the energy level for the nanoparticles for such excitation now becomes discrete like atoms, and these depends on the size. So you can imagine that if you can control the size to the precise size, then you can control the excitation energy relatively easily. For mechanical properties, first of all, nanoparticles is very small, so therefore it has lower probability to form defects in size. So majority of nanoparticles should have higher strength, or should have the strength approaching theoretical value, okay, because they have low probability to form defects inside. So if you have lower probability to form defects, the stress inside the nanomaterial is usually very small. So that should give you higher strength than conventional materials. People have said that carbon nanotube has very high strength. It can withstand the weight of a car. Okay, something like that. Last one is electrical properties. On one hand, conductivity of nanomaterials is enhanced by better structure or less defects. If you have lower probability to form a defects inside, the conductivity will be enhanced. But on the other hand, surface area of nanomaterial is very large, and you can lose electrons from the surface. So conductivity is also decreased by surface scattering, these two factors are offsetting each other. So depending on how you control this one, okay? For nanomaterials, there are two general form or general groups of nanomaterials. The first one is material in nano size, like nanoparticles, nanofilm, nanofibers. But also you may have materials with nanoscale feature, just like porous materials, material with a lot of holes. But if the hole size is in nanometers, it's called nanoscale holes. In general, this material is called mesoporous materials. Okay. Example of mesoporous material is zeolite. In this picture, this is atomic arrangement of zeolite. Zeolite is aluminum-based and silicon-based material. Okay. Each corner here is atom. These atoms form a cage. Inside the cage here, in the middle, is a void, is a hole. So you can put anything inside. So zeolite is considered porous material, but the porosity of zeolite is order. So we can use this in a clever manner. For instance, if you disperse metal which are catalysts around zeolite, you can use the high surface area of zeolite as your advantage. On the other hand, if you put these metal catalysts inside this cage, like this picture inside the cage, the opening of this zeolite cage can screen the size of the reactant accessible to the catalyst inside. So you can use the structure of the zeolite to screen reactivity of your reactant. Alright? For instance, if you have crude oil and you want to react some small molecules to something else, and you do not want reaction to take place for the large, bigger molecules, you can put catalyst inside this small opening of zeolite that only small reagent can access to this catalyst and undergoes conversion. Okay. Recently, there's another form of porous material. This is called MOF, standing for Metal Organic Framework. Okay. In zeolite, all atoms are inorganic. For MOF, the structure right here, some of them are organic molecules. Okay, and the porosity is even higher and more controllable than zeolite. So this is hot issue right now. In material with nanoscale feature, there also includes material with nanopatterning. For instance, you can make lines on the surface, you can make hole on the surface, you can also make features in various forms like this. They have several applications. Okay, for instance, the pattern like this, the pillar form pattern, can give you hydrophobic features on the surface like lotus leaf. Okay, so you can make the surface not wetting to any liquid, and that would be advantage in many manners. You can also use this pattern to control proliferation of the cells, so that you can grow particular cells in particular way. You can also provide electrical stimulation to the cells through this small wire as well. So the advantage or the applications are endless. In this course, we are going to discuss fabrication of nanoparticles or nanostructure materials depending on the size or dimension. The first one that we will discuss would be zero dimension nanostructure. Zero dimension means no dimension in the particles that is non-nano size. In other words, all size are nano size. like this: nanoparticles or nanocrystals. It also contains or considered quantum dots. For one-dimension nanostructure, this structure has one side to have size that is not nano size. Okay, so it is large in one direction, small in two directions. That would be wire, fibers. Okay, these fibers or wire has diameter in nanometer scale, but the length can be centimeters, can be meters, even endless. For two-dimension nanostructure, we have only one side to be nano size. Okay, that would be considered thin film, a very thin film covering the surface. We can also do patterning on the film. These three nanostructures will be learned in this course. The way we fabricate nanostructure materials, we can do either top-down. That means starting from very large materials, trying to make the size smaller and smaller. The easiest thing to imagine is doing grinding. Okay, you pound. You do the pounding on materials to get smaller and smaller and smaller. That's one way to do it. It is called top-down, starting from big down to small size. But more popular approach would be bottom-up, which start from atoms and make atoms groups into particles and end up with nanomaterials. This is a relatively easy way to do, but the tricky thing is how to stop agglomeration of atoms or agglomeration of particles at nano size. And the trick that we will learn in this course is in here. How can we stop at the right size or the desired size? These two can also be divided into two categories: physical approaches and chemical approaches. Okay, for fabrication. Physical approaches is like milling. You just mill until it's smaller and smaller. That's also possible, and some people do the milling to create nanoparticles. Okay, you can do evaporation and quench. Just evaporate your reactants or evaporate your solid sublime into vapor and quench them quickly. You will end up with nanoparticles. These are considered physical approaches because inside the technique there is no chemical reaction at all. On the other hand, if you use chemical reaction, they are considered as chemical approaches. In this course, we will focus mainly on chemical approaches, which are basically a bottom-up approach. Alright? So, this is the first chapter or the first lecture for introduction of nanostructure materials. And next lecture, we will start by talking about physical properties and physical chemistry relating to the fabrication of nanoparticles.